Gastón Brusasco, and today I will present my work, Magnetic Chain Interaction in Spinels-like Ferrites and Chromides of Zinc and Cadmium, a comparative DFT study. Before I begin, please excuse me my English. What is the problem? In this paper, Jaresco reports for chromate cadmium different sign of J1 with U. J1 is the coupling constant to first neighbor magnetics. For another way, Pandey report the problem, the ferromagnetic and antiferromagnetic configuration differ in magnetic moments, and therefore decide to constrain the magnetic moment in his calculates. In our work, we don't have these problems. Study system, DFT, and Heisenberg model. The ferrites and chromides have a normal crystal structure where the magnetic cation occupy the octahedral sites, color blue, and the non-magnetic cation occupy tetrahedral sites, violet color. The red points are oxygens. These compounds have application and interest in spintronics. For this study, we used density functional theory. DFT is used to study materials by determining their structure, electronic structure. And for another way, the model Heisenberg analyzes magnetic interaction with this Hamiltonian. Here, J is the coupling constant, and if J is positive, the magnetic interaction is ferromagnetic, and if J is negative, the magnetic interaction is antiferromagnetic. Methodology. We use two methodologies. First, full potential momentum, in the method full potential momentum plane wave with the code Win2K with this parameter of calculate. And for another way, the method of pseudo potential and plane waves in the code quantum express with these parameters for the calculation. In both cases, we use PBA, GGA for exchange and correlation. Up to which order of interaction in J you'll be considering. Here, we can see for ferrite of cadmium an excellent agreement between energy by DFT, red circle, and energies for Heisenberg model, black cycles. Here, with this coincidence, see, therefore considering interaction as to third neighbor is enough to describe the magnetic behavior of this compound. This trend is observed for all compounds in the study. Here we have J for all compounds. In this case, for both ferrite zinc, and ferrite cadmium and chromate of zinc, we see the similar behavior for the coupling constant J1, J2, and J3. See, J is the coupling constant to the neighbor, for example, J1 coupling constant first neighbor, J2 second neighbor, and J3 third neighbor magnetics. See, excuse me, here, or another way, in this case, in chromatic camion, J2 and J3 shows similar behavior and the other compounds, but J1 increase your value with U. This behavior is not expected. Here we see two methods. Here, exchange coupling constant with quantum espresso, and here, exchange coupling constant obtained with Win2K for the chromate of cadmium. Here shows similar trends in both methods, but with a strong quantitative difference. Here and here, J2 and J5, J3 present similar behavior, but J1 a similar behavior, but with different behavior, different change of sign. Here, we see determination of magnetic exchange parameters J with fixed geometry. In this case, all atomic position is fixed, and the four systems were calculate an identical atomic position with a reference here, the chromate of zinc. We can see that the main variation of J occur when changing the magnetic cation. Here, for example, chromium for iron, J1 increase almost double. Yes. And here, chromate cadmium, chromium change for iron, J1 increase your value. In this case, chromium and chromium, see, yes, change zinc for cadmium, the J is very similar in both cases. All calculates for make an identical atomic position. And then here, the magnetoelastic effect. The magnetoelastic effect refers to how the structure responds to the system change in the magnetic configuration. Here we can see for chloride of cadmium, the behavior, the constant coupling J in the case fixed atomic position. And here we can see chloride of cadmium, but relaxed atomic position. In both cases, the graphics are very, very similar. This implies no exit magnetoelastic effect in this case. For another compounds, we have the similar, the same behavior. Conclusion: no magnetic effect is observed. The difference between fixed and relaxed atomic position do not significantly modify the exchange constant J. Ferrite zinc ferrite cadmium, and chromium zinc show a similar evolution of the exchange constants J with U, with mostly quantitative difference. Chromate cadmium show magnetic behavior that differ from the other compounds and remains not fully clarified. Further investigation is required. The behavior obtained using ultrasoft pseudopotential for chromate cadmium appears less reliable than expected, suggesting that its description within what quantum espresso may require additional testing or alternative and computational approach. Thank you for attention, and special thanks to our organization committee for the opportunity to present my work. Thank you.
Thank you, Gastón, for a very nice presentation. So I think we have time for one quick question. So if you can raise your hand if you have a question. Actually, I think we have one in the chat. So John Fullerton asks, could you expand on what the applications of these materials could be, and are there different benefits to chromium and iron compounds?
These materials have application in sensors, high pressure, catalysis, high and spintronic, but I don't know exactly how chromium and iron influence in this behavior.
Okay, thank you, Gastón Brusasco.